Yeah, so I talk about this relative quantum cohomology under birational transformations. And also, I don't see anyone from my screen, so if you have questions, you just ask, because I cannot see other things from here. Okay. Yeah, so this is the outline of the talk. So I want to talk about how relative Gromov-Witten theory varies under birational transformation. So first of all, I will review this how Gromov-Witten theory, how absolute Gromov-Witten theory varies under birational transformations. In particular, is the Krapin transformation conjecture, and then here we'll get a motivation of why we want to study this relative Gromov-Witten theory and how relative Gromov-Witten theory under birational transformations is related to the classical Krapin or disk-Krapin transformation conjecture. And then there are some connections with some other things like extremal transitions and FJRW theory. We will talk about this in the end. Okay, and so first, how Gromov-Witten theory varies under birational transformations. Let me briefly give a review of the definition of Gromov-Witten theory and some basic properties of it. So Gromov-Witten theory is a curve counting theory, but to define it, we are not just studying the curves, we study maps from the curve to some target varieties. So what people do is to define this moduli space called the moduli space of stable maps that comes objects like this here. Have a curve with some markings and a map to the target variety. And the push forward of the fundamental class is this, the curve class, and it's called stable map because the automorphisms of the map will be finite. And so this is a moduli space, and Gromov-Witten theories are Gromov-Witten invariants are some intersection numbers on this moduli space. And the precise definition is like this. We have some cohomology classes, and they can pull back by the evaluation map. So I didn't talk about what is evaluation map, but there's a map from this moduli space to the target X. The image of the map is the image of these markings. So if we have a map like this, then the evaluation map takes this to FPI. And so we can pull back some cohomology classes to the moduli space and then intersect this with the fundamental class of the moduli space. It's the intersection number. This means virtual fundamental class because in general, this moduli space has no fundamental class, but there's a construction called a virtual fundamental class that can be used as a replacement of the fundamental class. We are not going into the detail of this today, but what we need to remember is just that this is an intersection number on this moduli space that comes maps to the variety X. And so one important property of Gromov-Witten theory is that it defines a quantum cohomology ring. It's written like this here, and it's a deformation of the usual cohomology ring using Gromov-Witten invariance. instead of the cut product, we can have something called quantum product. Oops. Quantum product, which is defined using a 3-point general zero Gromov Witten invariance. So the quantum product is written like this. When d is 0, then we just get the usual cut product. So it's this quantum product is the usual cut product plus some extra terms that are given by Gromov Witten invariance. So it's a deformation of the usual cohomology ring using Gromov Witten invariance. So to study quantum cohomology, one way is to do mirror symmetry. Mirror symmetry is a duality between two spaces of two kinds of geometry. So called A model and the B model. The A model geometry, and here is the Gromov Witten invariance. So the statement is that we have a generating function of general zero Gromov Witten invariance, which is called a J function, and this will be related through mirror symmetry to the B model of the mirror space, and the B model object here is the period integrals called the I function. So the I function of the mirror is related to the J function of X, and the statement of the mirror symmetry is that this A model function, J function equals the B model function, I function, and there's a change of variable tau y. Here it's called a mirror map. And for example, the I function for 23 folds, it is explicit hypergeometry series. You can write it down like for more complicated targets like toric compensations or toric orbifolds and other more complicated spaces. You get some explicit formula for this function, and that this is a way to start to compute Gromov Witten invariance, because Gromov Witten invariance in general are difficult to compute, and by mirror symmetry they are equal to this explicit formula, this explicit function, so that can be used to compute Gromov Witten invariance. And quantum cohomology can be reconstructed from this I function. So to study quantum cohomology, we can just study this kind of explicit function. One classical question in Gromov Witten theory is that how Gromov Witten theory varies under birational transformations. Gromov Witten invariants are deformation invariants, but they are not birational invariants. So that's a question that people have been asking for like 20 years maybe. And there's an explicit conjecture by Yongbin Wang. It's called the Krapin transformation conjecture. Yeah, it says that if there's a Krapin transformation, so if x plus and x minus, they are birational, and there's a x tilde, and there's they are projective birational morphisms from x tilde to x plus and x minus. Its Krapin means that they are k equivalent that satisfy this equation. And then the conjecture says that if we have a Krapin transformation like this, then the quantum cohomology of x plus and x minus should be the same. Not exactly the same, but it's under some analytic continuation. Then these two these quantum cohomologies will be the same. And since this quantum cohomology can be determined by the I functions, these I functions, if you remember from here, it's some explicit hypergeometric function. And so there's analytic continuation that relates one of the I function to the other I function. It's basically how to prove the Krapin transformation conjecture. So there has been a lot of work about this conjecture, like conjecture by Ron, and then there's some work by Coates, Ron, and Li, Ling, Wang. They have a lot of papers on this. And the one paper that I'd like to talk about briefly is the paper by Coates, Iritani, and Jian. And they prove this conjecture for totally complete sessions using the I functions. So for totally complete sessions, they have I functions, and they prove that these I functions are exactly related by an analytic continuation. So that was the Krapin transformation conjecture. You can also consider in the case when you have these Krapin transformations, it's when we have this inequality instead of equality, and the opposite of the Krapin case is this Krapin. So there are some work about this, not so many work on this conjecture, on this Krapin case, but there are some work by Iritani and Costa Shoemaker. The papers by Costa and Shoemaker says that this is the relation between the quantum cohomologies like this. You look again. You look at the I function, some explicit function, right? The relation is that the Laplace transform of this regularized I function of x minus can be analytically continued to the I function of x plus. So what they need to do is first regularize one of the I function and then do some Laplace transform and then do analytic continuation. Then you can relate them. And it's like if you don't know what they do here, it's okay because it looks too complicated, right? The relation in the discrepant case is a lot more complicated, more difficult than the Krapin case. For the Krapin transformation conjecture, we just need to do analytic continuation, but in the discrepant case, there are some extra things that you need to do. So the question is like, is there an easier approach to this question? I mean, for the discrepant case, my proposal for this is that we have discrepant transformation, but we can try to make it into a Krapin. In some sense, we can try to get some divisors, d plus and d minus, such that we have an equality instead of an inequality. Then to compare the relative quantum cohomology of the pairs of x plus, d plus, and x minus and d minus. We hope that comparing relative quantum cohomology will be easier. And as we see in the previous slides, like the discrepant transformation conjecture would be like much more complicated. Okay. Now, this is the motivation of why we need to study Gromov-Witten invariance of pairs. So also in here, we have D plus and D minus, but D can be smooth or simple normal crossings. There's no like particular restriction of what D should look like. So this gives a motivation to study Gromov-Witten invariance of these pairs. That's why I'm here. Now here I'm going to define this relative Gromov-Witten theory. The definition is similar to absolute Gromov-Witten theory, but instead of just counting curves with tangency conditions along a divisor, so the target is a variety with a smooth divisor, and some extra data ki here that because the tangency condition along the divisors. So there are some extra markings of the curve that records the tangency condition. That's the difference from the absolute Gromov-Witten theory case. Then one can define this moduli space of relative stable maps. The definition of this is more complicated, but there is a definition. There is a moduli space called a moduli space of relative stable maps with some markings and genus G and degree D. And these have some extra markings here that we call the tangency condition. And then the definition is that again we have evaluation maps, and for some we have some markings that has these tangency conditions. So these markings were mapped to the divisor D because they intersect with the divisor. And there are some regular markings like what we have seen earlier for absolute Gromov-Witten theory. This just here is just some regular markings. So there are two types of evaluation maps. You can pull back some cohomology classes from D and X, and then again, the definition is similar to absolute Gromov-Witten theory. Just intersect, we just pull back these cohomology classes by the evaluation maps, and then intersect with the virtual fundamental class. Then we get a number, and this number is a relative Gromov-Witten invariant. So the definition is similar to the absolute case. And one can also define a quantum cohomology structure, which we call relative quantum cohomology. And again, the definition is similar to the absolute case. I'm not going to write down a formula here. There's also a mirror symmetry statement for Gromov-Witten theory of a pair, and there's also an I function. And this, so in this paper, we have an explicit formula for the I functions. It may look a little bit complicated because this has this called JXD. This is a J function of Gromov-Witten theory of X. Yeah, and if you know about mirror symmetry statement for X, then you can replace this by some explicit hypergeometry series. So then the point here is just that there is an explicit I function, like in an absolute case, and we can study that for the relative quantum cohomology. There's one remark here that this relative Gromov-Witten, there's another way that you can define relative Gromov-Witten theories to think about it as certain limit of some orbifold Gromov-Witten theory. So this orbifold is called a root stack. It has is smooth away from D, but it has generic stabilizer of mu R along the divisor D. You just put some orbifold structure on the divisor, and that can define. You can use this orbifold to define a Gromov-Witten theory, orbifold Gromov-Witten theory, and that orbifold Gromov-Witten theory will be the same as relative Gromov-Witten theory when this root R is taken to be sufficiently large. And this can be used to generalize the definition of relative Gromov-Witten theory to simple normal crossing pairs. The previous definition of relative Gromov-Witten theory is just for the case when we have one D has one irreducible component. But to generalize that, we can use this orbifold definition. We look at some orbifold. We can have root construction along each of the irreducible component of the divisor, and then take this root to be sufficiently large and to get some Gromov-Witten theory of the simple normal crossing pair. Yeah. So yeah, you can define this. So in the paper we call this Gromov-Witten invariance of infinite root stacks, because it's a limit of this root stack. For this kind of Gromov-Witten theory, this occurs with tangency conditions along simple normal crossing pairs. And there's also a quantum cohomology ring for this kind of relative or orbifold Gromov-Witten theory. We also call this relative quantum cohomology for simple normal crossing pairs. So if you know about log Gromov-Witten theory, then this log Gromov-Witten theory is another way to define Gromov-Witten theory of simple normal crossing pairs. And in general, this definition from orbifold, this orbifold definition that we just talked about, in general, it's different from the definition of log Gromov-Witten invariance. And the major difference is that log Gromov-Witten invariants are invariant under birational transformations, but this orbifold invariants that we just defined, they are not invariant under birational transformation. So there's another motivation, another question here is that what exactly is the do we still have some kind of birational invariance of this kind of orbifold Gromov-Witten theory? Not on the level of a single invariant, but the quantum cohomology, relative quantum cohomology of this kind of pair. So that is another motivation of why we need to study relative quantum cohomology under birational transformations, because in this way we can see how these invariants are different from the log Gromov-Witten invariance. Okay, so there are basically two motivations to study this topic here, relative Gromov-Witten theory under birational transformations. One is that it's a classical question from the Kraepelin transformation conjecture. That's why we need to study this, how relative Gromov-Witten theory under birational transformation. Another reason is that there's a relation, can tell us a relation about between orbifold, between this kind of relative Gromov-Witten theory and log Gromov-Witten theory. Okay. So let's go back to the setup here. We have a birational transformation between x plus and x minus, and they can be discrepant. And what we do is to consider divisors d plus and d minus, such that we have an equality like this, which is, I call this log k equivalent. Then the question is how to relate Gromov-Witten theory of these two pairs. In the spirit of the Krapin transformation conjecture, there should be some form of birational invariance of this kind of Gromov-Witten theory, relative Gromov-Witten theory. And for example, like if we look at root constructions, this like XDR is a root stack, then there's a map to the coarse moduli space X. Then this is also an example of a discrepant birational transformation. It like replace this D by a root, a gerb of D, and this is actually like really blow up along the divisor D. So it's a discrepant transformation. And the relation, if we compare this invariance of this root stack and the invariance of X, then there are some relations says that this orbifold Gromov-Witten invariance can be determined by Gromov-Witten invariance of X and Gromov-Witten invariance of D and the restriction map of the cohomology. But if we look at the relative Gromov-Witten invariance, then the relation is much easier. Then they have a direct identity between this relative invariance of this root stack and relative invariance of X. And the reason is, like one reason you can see that is that if you look at the complement of the divisors, then they are the same. Right? And so the relation between relative invariance should be like are simpler than the relation between absolute invariance. So this is for the example of a root construction. So in general, we should expect that the relation between relative quantum cohomology is usually easier than the relation between the absolute quantum cohomology. Yeah. So let me talk about the explicit setup of this. Explicit example of this. So an example is the example is blow up. It's a if X plus is a blow up of X minus along a complete intersection center of D minus 1 intersect intersect D minus n, then what we can do is that we can choose this D minus to be in a simple normal crossing divisor of this di's here, and then we can choose D plus to be this street transform of each D minus I, and plus the exceptional divisor. Then in this way, we can have the equality of like log k equivalent. And you can check that if we choose D minus and D plus in this way, then we will have that equality that in the previous page here. We can have, and we will have this equality. compared to this example. Another way that we can choose is that we can choose these divisors to be smooth divisors, and then also satisfy the same equality. Then we can try to compare the relative quantum cohomology. So there are two cases that we consider here. Of course, you can choose other divisors as long as they satisfy the equality. Yeah, but in here we just talk about these two cases. And a more precise setup is we can consider the toric wall closing case. So toric varieties or toric manifold stacks can be defined as GIT quotients with a choice of stability condition. I'll give an example on the next page. There is a wall and chamber structures in the secondary fan, and a single wall closing gives a birational transformation between toric varieties. Example is a toric blow up along a complete intersection center of toric divisors. Example is like this. So this is a picture of the secondary fan of blow up of P2 along one point. So this line, horizontal line here, is the hyperplane class of P2, and blow up along one point. So we get two divisors of x minus e, and e is an exceptional divisor. And the secondary fan of this blow up of P2 is like this. So this now there's a OR. So these three lines here, they are ORs, and this you have chambers, omega plus and omega minus, and this omega plus chamber will give a definition, will give this x plus, toric variety x plus, which is the blow up of P2, and if we choose a stability condition on here, omega minus, then that gives variety P2. And the wall closing is go from this plus chamber to the minus chamber. That gives a toric wall closing, and that gives a birational transformation between x plus and x minus. So yeah, that's the example. And yeah, in general, like we can have more complicated toric manifold stacks, and like there's a more complicated toric wall closing. In general, like what we will have is that if we have a birational transformation like that for between toric manifold stacks or toric complete intersections, then we can choose these divisors d plus and d minus in a case such that these toric divisors containing the loci of indeterminacy are the irreducible components of the divisor, which means that if we take the complement of x plus minus d plus, it will be the same as x minus minus d minus, and the complement of the divisors of these two pairs are the same, and it's natural to expect that the Gromov-Witten theories are the same. And the result is that if we look at the I functions for these two pairs, then they are exactly the same, and they can directly identified with R during any analytic continuation. Now, for the absolute Gromov-Witten theory, if we try to relate the I functions, for example, even in the Krapin transformation case, we need to do some analytic continuation in order to relate Gromov-Witten invariance of x plus and x minus. But if we do relative quantum cohomology, then the relation is directly obtained without any analytic continuation. So that's one evidence that shows that in general this relative quantum cohomology should be easier when we consider these birational transformations. And that's the case when we have simple normal crossing divisors. But we can also have like two smooth divisors. We can take some smooth divisors such that we have the k-equivalent relation. To study that, one can use this one of these two results called a local relative correspondence or relative orbifold correspondence. I will just talk about the first one. That this local relative correspondence means that if we consider a smooth pair, then the relative Gromov-Witten invariant in general 0 with a maximal contact order would be the same as general 0 Gromov-Witten invariance of the total space of the bundle. So to study Gromov-Witten theory of the pair, you can study Gromov-Witten theory of the total space of the bundle. And there's a generalization of the result, which it's not important right now here. So you can study the Gromov-Witten theory of the total space of the bundle, and the advantage of that is that you can again look at the total picture. This is again P2 blow up 1 point, but if we look at the total space of the canonical of the bundle, like minus d plus, then what we have is we have an extra divisor here, extra line here, and that corresponds to this minus d plus, and now this will be the secondary fan for this OX plus minus D plus. And you can now this is again a wall closing structure, and this wall closing will become Krapin wall closing. Yeah, so this is a omega plus, omega minus. This omega plus gives the definition, gives the total space of the bundle of OX plus minus D plus. And this omega minus, it does not give this OX minus minus D minus. It gives another toriality, which is called T minus bar, is a partial compactification of this OX minus minus D minus. Yeah, now the relation between this total space of the bundles is that you can study the I functions or relative quantum cohomologies or relative of these quantum D modules of the total space of the bundle, and they are related by analytic continuation and specialization of a variable. And the analytic continuation is the relation between this T plus and T minus bar, and the specialization is go from this compactification to this bundle. So from plus to minus is the analytic continuation, and from this inclusion here is related. It gives the relation of the specialization of one of the variable. So this result follows from this result proved by me and Shoemaker. So that implies that if we study the relative quantum cohomology of the pair, then they are also related by analytic continuation specialization. So in the paper of me and Shoemaker is that they study this canonical, and they study this total space of the bundles. And that's not important here now. And now let's talk about the relation with extremal transitions and FJRW theory. So I talk about this paper by me and Shoemaker. What they study is the extremal transition, how Gromov-Witten theory varies under extremal transition. And let me briefly explain what's this extremal transition. So two projective varieties X and X tilde are said to be related by extremal transition if they are related by a birational contraction and a smoothing. There's a famous Reese fantasy that says that any pair of smooth Calabi-Yau threefold may be connected by a sequence of flops and extremal transitions. So in some sense, if we know about Gromov-Witten theory, if we know how Gromov-Witten theory varies under extremal transitions, then we just need to study Gromov-Witten theory of one Calabi-Yau threefold, and we will know about the Gromov-Witten theory of all the Calabi-Yau threefolds, of any Calabi-Yau threefolds. An example of the extremal transition is called a cubic extremal transition. So let S be a cubic surface in a Calabi-Yau threefold, and if there is a birational contraction, so y tilde to x0, such that S is contracted to a point, and the local equation is like this. Now we can deform the local equation to get another Calabi-Yau, and it's called y, and the relation between y tilde and y is extremal transition. It's called cubic extremal transition because we contract a cubic surface here. More specific example is if we have a quintic threefold in P4, and the X is P4, X tilde is a product of P4 along one point, then we can take Y tilde as the smooth Calabi-Yau hypersurface defined by a divisor 5H minus 3E. So E is the exceptional divisor. Now this is a cubic extremal transition because, like, if we look at the exceptional divisor of X tilde, it's a P3, right? P3, in this Y tilde intersect with the P3 is we have 3E here, so it's a cubic surface, and the cubic surface was contracted by the blow-down map from this blow-up to P4. So this is why the cubic surface is contracted, and then we smooth that out, we get a quintic threefold. Yeah, that's an example of a cubic extremal transition. I can see that it's quite similar to the setup that we have. My X tilde is a blow up of P4, and it's a birational transformation. And then we look at the divisors on the hypersurfaces, and these hypersurfaces are related by extremal transitions. There have been a lot of have been some work about these extremal transitions. For some recent work, there's a paper by Rongxiao Mi that use this mirror symmetry to study cubic extremal transitions. That means he studied the I functions of the Calabi-Yau threefolds and then relate the I functions. And then there's the paper of Me and Shoemaker that generalizes this case to toric combinations. So let me talk about the setup of Me and Shoemaker. What I have is you have a toric blow-up, and then they take hypersurfaces D tilde and D smooth hypersurfaces such that D tilde and D are related by extremal transitions, and this is exactly the case when the pairs, these two pairs, are log k equivalent, and that's why our result is related to theirs. And they prove that the quantum D modules of X tilde and of D tilde and D are related by analytic combination and specialization of variable. What they do is, when the way they prove is through this quantum cell duality that relates Gromov-Witten theory of the hypersurface with the Gromov-Witten theory of the total space of the bundle. So what they actually prove is that to relate Gromov-Witten theory of the total space of the bundles, and this total space of this bundle is Gromov-Witten theory of this total space of the bundle is related to the relative, is the same as the relative Gromov-Witten invariance of these pairs. So that's why we just directly use this result. Yeah, again, that's an example that you can think about. It's the cubic case, like X tilde is pro alpha P4 and X is P4. You take hypersurfaces, the Calabi-Yau hypersurfaces of this X tilde and X, and they are related by extremal transitions. And yeah, and you can also study the relative Gromov-Witten theory of P4 relative to a quintic, and relative Gromov-Witten theory of X tilde relative to its anti-canonical divisor. Then that's the result that we have. Now a question for the extremal transition case is that there's a rank discrepancy between the I functions on the quantum cohomologies. That's because there's a contraction, right? From like Y tilde to Y, there's a contraction. So Y tilde, there are more curved classes on Y tilde. So there are more Gromov-Witten invariants on Y tilde than on Y. And so there's a rank reduction. You can study the Gromov-Witten, the quantum cohomology, and there's the I functions are solutions to some Picard-Fuchs equations, and the Picard-Fuchs equation for the so in here it's an example of the on the previous page. Here, Y tilde is this hypersurface in the blow-up of P4, and Y is the quintic, and the ambient quantum D module of Y tilde is of rank 6, and for the quintic is rank 4. There are two extra solutions for the Picard-Fuchs equation. It's coming from the analytic continuation of the I function of the Y tilde. And the result of Shoemaker that says that the rank reduction can be explained as the von Java's Witten theory of the cubic singularity. But I'm not going to talk from the definition of this FJRW theory, but this definition is also a construct modular space and studying intersection theory of that. It studying the it's called quantum singularity theory. And the two extra solutions after specialization recovers the regularized FJRW of the cubic singularity, which makes sense because in this process we have a cubic singularity, right? And this cubic singularity should be responsible for the rank reduction. But the question here is that we just talked about Gromov-Witten theory, right? So that it should be possible to give an explanation of the rank reduction directly in terms of Gromov-Witten theory. That's what I want to say here. So in the paper by me, the statement basically says the I function of y tilde equals the I function of y after an analytic continuation and specialization of one of the variable to be 0. And now if we can think about this in terms of Gromov-Witten theory, is that this I function of y tilde, if we specialize the other variable to be 0, then that is exactly the I function of the canonical bundle of the cubic surface S. And this cubic surface is the subvariety that was contracted by the extremal transition, right? This S is or gets contracted, and so the this Gromov-Witten theory of S on the total space of X, S on the normal bundle of S should be responsible for the rank reduction because this is the pod that gets contracted. So in general, if we have toric hypersurfaces d tilde and d are related by extremal transition, and if S is the subvariety of d tilde that is contracted under this transition, then the rank reduction should be explained as the local Gromov-Witten theory of the total space of the normal bundle of this subvariety that gets contracted. Right, because Gromov-Witten theory comes curves and this variety gets contracted, so the curves in this S is responsible for the rank reduction. But another question here is why in Me's paper there's this FJRW theory here. And let me briefly talk about this relation with the FJRW theory. So FJRW theory is another theory that's defined as similar to the Gromov-Witten theory. And for Gromov-Witten theory of Calabi-Yau hypersurfaces in weighted projective spaces, you can define an FJRW theory. And there's Landau-Ginzburg Calabi-Yau correspondence that says that the Gromov-Witten theory of the Calabi-Yaus should be the same as the FJRW theory under analytic continuation. Again, the relation can be proved using the I function of Gromov-Witten theory. There's also an I function for FJRW theory. There's a generalization of that beyond the Calabi-Yau case, to the Fano case, and general type case, and that's a paper by Acosta that says that there's a complicated relation by the Laplace transform and the regularization of the FJRW I function and then analytic continue to the I function of the Gromov-Witten theory of the final surface. And so there's a case for the final case, and the rank reduction. Now, the rank reduction in the qubit streamer transition case that can be explained as the FJRW of qubit singularity and also the relative or local Gromov-Witten theory of the qubit surface. And the relation here can be understood as a version of the Landau-Ginzburg final correspondence or Landau-Ginzburg-Calabi-Yau correspondence. Because like when we look at mirror symmetry for final varieties, what we actually mean is that the mirror is Landau-Ginzburg model, a variety with a function W, and but in general, it means that the generic fiber of this W is mirrored to a smooth anti-canonical divisor of X. And so the statement for mirror symmetry for final variety should be like this. If you look at a log-Calabi-Yau pair, and this log-Calabi-Yau pair is mirrored to the Landau-Ginzburg model. So whenever we talk about mirror symmetry for final varieties, we should think about mirror symmetry for log-Calabi-Yau pairs instead of just the final variety. And so the FJRW theory. So for final hypersurfaces with smooth anti-canonical divisor, there's you can have a Landau-Ginzburg-Calabi-Yau correspondence that relates this relative Gromov-Witten theory with the regularized FJRW theory, and like in the case of the qubit streamer transition, the relative Gromov-Witten theory of the qubit surface is related to the FJRW theory of the qubit singularity, and that's but we don't have an explanation for this like regularized FJRW function yet, but there should be a like Landau-Ginzburg log-Calabi-Yau correspondence, and that's what we have in here. Okay, yeah, that's it. Thank you.